Hi guys, this is Madhav. I have a very simple seeming problem here. I want to put together some kind of sensor that will take a gear and after it spins, tell me what is the revolutions per minute of this gear, i.e. measure the rotational speed of the gear. This kind of simple idea has kept me iterating for weeks as I figure out what are the best sensors that will help me in my particular use case. But the approach in general, it's kind of simple. Basically, you have our very artistically drawn gear over here, or any kind of wheel with spokes in it, with holes, gaps in it. And on one side, you put some kind of laser emitter or infrared light emitter or just an LED, just a light source to get through the gaps in the wheel. And on the other side, you have a light sensor. With this, you can make a simple electronic circuit that will keep emitting light source on one side, keep detecting light source on the other, and whenever the spokes of the gear or the wheel come around, then the light emission or light detection stops, and you know that a part of a rotation has happened. You can of course vary this a little bit, so you can use any of these components. Personally, I found a laser easiest to use, but maybe you could also make it work with an ultrasound sensor. You just have to adjust for the distance that the ultrasound waves are traveling, and it might be a little bit slower just because sound is traveling slower than light. Also, you could have, if you don't have a wheel with gaps in it, you could just have a full-on disc and just attach like an aluminium sticky patch on one side that a laser bounces off to a detector. Similarly, maybe you have a magnetically active material that's applied here, maybe some iron, and you can detect changes in the magnetic field as the wheel rotates and this patch comes to you. So the basic idea is simple. You just have some kind of emitter of some sort, maybe magnetic, maybe light, maybe sound, and then you have a detector to measure changes in that emission as the wheel continues to rotate. With that being said, let's talk about the circuit that I specifically created. So here we have the circuits that we're going to be using. As you can see, it's just got two parts, one on the right, which is a light emitting probe. Again, you can replace that with some other kind of emitter. And on the left, you have some kind of sensor. So in this case, I have a photoresistor. And because the Arduino can't measure changes in resistance for the photoresistor, we have a standard voltage divider circuit to change that resistance, that variability, into changes in voltage that we can measure. So on the emitting probe side, here I have shown an LED. You could have a laser. It's a pretty simple circuit. You just have one input that is supplying power and the other goes to ground. On the other side, you again have the red line here. It is the power input. It goes through a resistor, and then before it can reach the photoresistor or the sensor, the other sensor that you're using, like an infrared receiver, before it can reach that device, you have the power, well, not the power, the voltage being measured through this green wire and going into an analog terminal. After that, the electricity carries on through. It goes through the photoresistor onto the other side and then back through to ground. With the key idea here being that you choose a resistance value that's appropriate for the resistances you expect, the range of resistance you expect from your sensor over here. A good rule of thumb is just take the average of the lowest and highest resistance values you expect. And an even better rule of thumb, if you're willing to look it up, is take the geometric mean. But in any case, the circuitry isn't too complicated. Hopefully this diagram is enough to follow along with. So now we'll move on to the code part of the sensor. Just an image to keep in your head. This is the gear that I'm using. As you can see, it has 1, 2, 3, 4 spokes. And there's going to be a laser that is firing from one end. It's going to go through the holes in this gear to a photoresistor on the other end that is going to receive the signals from the laser. Just something to keep in mind. The thing that you'll see me doing in the code a lot is I'll be tracking the time that a laser signal is interrupted. The reason I'm doing that is because the laser is going to go straight through my gear until the spoke gets in the way. So my code is going to have a lot of sections where I measure the time that the spoke gets in the way. Because if the laser is coming through, and then it gets interrupted by the spoke, because I have exactly 4 spokes, that tells me a quarter rotation has occurred for my gear. So that's why I'm tracking the time that it takes for that rotation to occur, because it can help me get the speed, which is what I want. So with that being said, let's start with just defining some key variables that I'm going to be using in my code. First of all, there's the obvious. We have a pin that we're going to be sending high voltage to for the laser. So it's going to be the transmitter pin. It's going to transmit the light. We're just going to leave it as high, and it's going to keep on shining the laser, though it may or may not reach the photoresistor pin if one of these spokes gets in the way or not. Next, we're going to create some variables that are going to track the time in milliseconds that it takes for the laser to get blocked. So whenever we have a change in the laser reaching the photoresistor or not, we're going to take our millisecond timestamp and we're going to put it in this array. It needs to be an unsigned log just because millisecond numbers are going to get very large. So that's why we have an array of this particular data type. Also, we have 4 signals that we're going to measure, 4 timestamps, because I have 4 spokes. So I'm going to measure the time taken to go from, the laser shining through to being blocked by the first spoke, then the next one, then the next one, then the next one. Of course, your wheel or your gear could be different. It could have a different number of spokes. So just wanted to put that out there. That's why we have 4. We have a particular variable called the last signal. What it's going to measure is whether you have a change, like the laser was going straight through and then it was blocked, compared to whether the laser was blocked and then it started going straight through. Because I only want to record a timestamp when we have the first kind of change, when the laser was going through, then the laser was blocked. If I did it for both, going through then blocked, and then also again for blocked then going through, then I'm not going to get accurate readings. So this is why we have a separate variable to keep track of the last time we got a signal. Also, we have some variables that we're going to be using to calibrate our sensor, that is, calibrate our photoresistor. We want to figure out what are the resistance values we get, or the voltages we get based on that changing resistance at the level of normal ambient light. This is going to vary, which is why we need to measure the level that we have when the laser is on, the level that we have when the laser is off. And then based on that, we're also going to calculate a threshold, which is just going to be the average of the 2 levels. So let's say, the level of the light sensor with the laser off is low, the level with the laser high is high. We're going to take a value in the middle, and if our photoresistor is giving values that are greater than the middle, then we'll just assume that the laser is on. We're going to work closely with these variables when we calibrate our sensor. So I'll show you that function in just a second. But the last variable we have here is exactly what I talked about. Do we have the change that I mentioned? You have the laser going through and then it stops. Not then it stops and then the laser going through. So we'll explain this in a bit too. Let's start off with these variables. We'll talk about the code that calibrates the sensor. So in my setup function, first of all, I'm doing just the obvious things. I'm setting the transmitter pin. I'm setting up communications that will appear here in a bit. But then the more unique part is I'm calibrating these levels. So first off, I will get the ambient light levels without the laser on. You can see I haven't set this pin high, and I just keep on reading the values I'm getting for the photoresistor. They're going into the analog pin. I'm just getting those values, and then I keep on averaging the values that I get. Every 10 milliseconds I do this. So I'm just going to track those average light levels without the laser on every 10 milliseconds for a bit. And then I will repeat the same thing with the laser now turned on. So I turn the laser on, and again, now I'm measuring the average light levels with the laser on every 10 milliseconds for a bit. So these will tell me what are the ambient light levels, what can I expect in this particular environment, whatever I happen to be in. And based on that, I will, again, as I mentioned, take the average of those two extremes and then use that as my threshold value. So down here, I'm just getting the threshold as an average, and I'm printing out the ambient light levels. So all this code was just set up. We declared a few important variables, and we specifically set up the pins, the communication, and got the ambient light levels in our environment. Now let's move on to working with these pieces of data, which are involved in making the measurements from the photoresistor. So here's what we're going to do in our loop function. First, we are going to check if the receiver, the photoresistor that's receiving light levels, if it is in a high state. By a high state, I just mean the light levels we're getting are greater than the threshold we decided for the laser to be considered on. If this is the case, if we do get a high signal and the last signal was not high, i.e., you had the laser, it was going through, but then it got stopped, that kind of change, not the other kind of change, only then will we record the last timestamp that we had, so the time at which this change happened. And we are going to use a separate function, which I'll show you soon. We're going to use a separate function to store that timestamp so that we can compute how quickly the rotation happened a little bit later. So this loop function, the key point is that it's checking if the photoresistor value is high. If it is so and it wasn't like that before, then we track the timestamp. We record when did that change happen. And I'll explain how we'll use this soon to compute what the speed of the gear is. Moving on to that part, computing what the speed of the gear is. So remember, we were creating the signal of 4 timestamps associated with each spoke, being turned around. So the track time function, all it really does is it waits until that condition is true. It waits until we have 4 timestamps, and then it will compute the speed. So here's what we do. First, we compute the size of the signals array. In my case, I had 4 spokes, so I know it's 4. In your case, it could be something different based on the shape of your wheel. So we're just computing, how many timestamps do we need to record based on the array that you've initialized above. Once we've done that, for each record in the array, if the record is empty, if it's just a default 0 value, then we will write our new time, the new timestamp, into that spot. However, if we get to the end of the array and all the values have been initialized, that means we have finished collecting 1, 2, 3, 4 measurements in my case. So that's when we're going to call this other function, which is actually going to compute the rotational speed. So just as a summary, all that we've done in this function is we keep on checking for non-zero values that are still left in the signals array. If it isn't entirely full with our new timestamps that are associated with each quarter turn of the gear in my case, then we keep on writing those values in until they've all been filled, and that's when we're going to compute the speed. So finally, last function, how do we actually compute the speed? In my case, it's kind of easy because every time I get a timestamp, the gear has turned a quarter turn. So if I just multiply that value by 4, then I get the time taken for a gear to finish a full turn, which is related to its speed. So in this log speed function over here, again, I'm getting the size of the array, and I'm figuring out what is the full turn duration by adding the duration, the period between each pair of timestamps. So just to be clear, visually, let's say that I get, this gear is at this bar, spoke, I guess, this gear. It interrupted the laser with this spoke at timestamp equals 10 milliseconds. And then over here, it interrupted the second spoke at timestamp equals 1000 milliseconds. What I'm doing in this code is I compute 1000 milliseconds minus 10 milliseconds. That gives me the time taken, the duration of time for this rotation to occur. How long did the gear take to go from this first timestamp to the second timestamp? So I'm computing this for every half turn in my case, and then adding it to the total duration for a full complete turn. Once I get this total duration for one turn, then I can turn it into RPM with this formula. Why? Because if it takes, if it takes a gear, let's say this becomes 4000 milliseconds, okay? It takes a gear 4 seconds to do one turn. Then the inverse of that, 1 over 4000 milliseconds, the inverse of that is how many turns can it finish per millisecond. So this is in units of milliseconds per turn. If I divide that by 1, so 1 divided by turn duration, that now flips those units so that we have turns per millisecond. Unfortunately, that's going to be a really ridiculously small number, turns per millisecond, which is why I don't do 1 over the turn duration. I multiply that by 60,000 to get the revolutions or turns per minute. Why do I multiply by 60,000? Because in 1 minute, there are 60,000 milliseconds. So if I can get the turns per millisecond as 1 over the turn duration, then multiplying that by 60,000 gives me the turns per minute instead of millisecond. So that's why I'm computing the RPM like this, and I finally just print the RPM. And finally, After I've printed the RPM, I go and reset all the signals. So I reset this array so that it's again a bunch of zeros. Again, the loop function will run. It will track, it will record the timestamps when the turns happened. The timestamps will again start filling up the array. When the array is all filled up, then we again go back to the log speed function. It computes the speed, resets the array, and we keep on going like this, where the array is waiting to be filled up. When it gets filled up, we compute the speed, and then we start the cycle all over again. Now finally, I just want to show you that, well, the code actually does work. So I started the code just a second ago. I'm going to restart it so you can see the logs right from the very start. So when I restart the code, the laser turns off, and it's going to perform the calibration first of all. And that's when you will see that at the start, the light levels received by this photoresistor, they were low. And then as the laser turned on, they were higher. Now you can see I'm getting some readings that aren't entirely accurate before I've started spinning the wheel, so there is potential for issues here. However, I'm going to try and get accurate readings by spinning. So you can see I have some level of baseline as I'm spinning slowly. I'm going to try and spin this faster and faster. You can see that there are some issues if my laser gets off of the photoresistor. However, we do have pretty accurate measurements at slow speeds when the laser is focused onto the photoresistor. I'm tied with a stopwatch and I was getting similar RPMs as to what it was telling me. Let me slow down here. The key challenge with the design that I have right now is just that you need the laser to be focused on the photoresistor. So to really focus to make sure that it isn't getting, it isn't moving the laser. Hopefully in an actual production environment, you could fasten the laser emitter or the light source of any sort very securely instead of just having random wood blocks that you're holding. But for the most part, this is good. It works better than I expected for such a DIY system.